Just 1 second, just going through some tech things. Okay. Amazing. Let's see. Okay. Thank you everyone for coming to this. I believe it's the 10th talk of the term and this final talk from the Cambridge University Physics Society. We are very excited today to host Professor Elias Kiritsis. Currently he is working both at Athens and in Paris. Sorry, not at Athens, at Crete. And Elias, I believe you did your undergraduate study in Athens and your graduate study at Caltech, and have since then worked at Berkeley, École Normale Supérieure, and the theory division at CERN, and you're now a professor at the Department of Physics at the University of Crete. Your research is concentrated in high-energy physics and cosmology with the use of quantum field theory and string theory. In particular, it focuses on non-perturbative physics of field theory and M theory, supersymmetry, and symmetry breaking, and instant suns in string theory, conformal field theory, gauge theories, black holes, and much more. Before I give it over to you, I should say that CUPS is proudly sponsored by Seamless, Riverlane, TTP, TPP, Define, Jane Street, and CGG, who help make this possible. I should mention that you can either ask questions by unmuting yourself and just asking the question, or by typing it in the chat. I will be keeping track of both the chat here in this call and the chat on the YouTube stream. And if there are any urgent questions, you can ask them during the talk. Or if they are not urgent to understanding, they will be taken at the end. Elias, I think that's everything, and I'll hand it over to you. Thank you so much for coming.
Thank you very much, Oscar, for inviting me to do this. Good evening, everybody. First of all, I would like to start by apologizing for my English. I suspect it will not be at the level needed for this talk, but I'll try my best. Second, as Oscar mentioned, if something is not clear, please stop me and ask. And finally, I'd like to start by saying that I'll try to guide you tonight through quantum gravity string theory and the structure of space and time. This is a talk basically targeting an undergraduate audience with not necessarily, although of course I'm talking to a university which is one of the best in the world, not necessarily assuming that people would have to know all the ingredients. So I will try to keep it simple with, of course, the danger of sometimes oversimplifying. So as you all know, 20th century was marked by the discovery of two central frameworks of physics. One is quantum mechanics, which is the mechanics of the very small, and the other is general relativity, that is also the modern theory of gravity. Using the framework of quantum mechanics, as well as the notion of fields and special relativity, the framework of quantum field theory was developed, and this happened over a large part of the 20th century. Quantum field theory is the language that describes the standard model of particle interactions. It describes the elementary particles and their fundamental interactions, and this includes electromagnetism, the weak and the strong interactions. The standard model contains the leptons, the quarks, the interaction carriers, which are the gauge bosons, and the Higgs particle. And as a model, it has been tested in multiple experiments for over 40 years, mostly in particle accelerators, and this with impressive accuracy. The most accurate prediction of the theory is the electron's gyromagnetic ratio. It agrees with experiment in the first 15 significant digits. The results are written here. 2 is the number predicted by Dirac's theory, and the rest, here you get the correction coming from experiment. This is the experimental error. This is the prediction of the correction coming from quantum effects from theory. It has also an error because this calculation is approximate. The two agree. We have also measured many times and independently more than 50 different observables, and they all agree with the theory. However, physicists believe that despite its impressive successes, the theory must change at higher energies or shorter distances. In some sense, the theory looks like this pencil that has been made to stand on its tip. The tiniest perturbation would make it fall. This impressive success of the Standard Model would make us believe that we master quantum field theory and we understand it in depth. However, this is far from the truth. If the quantum fields interact weakly, then we have calculational techniques, and this is known as perturbation theory, to calculate observables that may be compared to experiments. It is in such weakly coupled theories that we understand the notion of a particle, which is generated by the quantum fields themselves. We can visualize the interactions of these particles as series of Feynman diagrams like the ones that you see here. Essentially, the Feynman diagram describes the interaction in terms of exchanges of weakly interacting particles. For example, here you have the scattering of two charged particles with the exchange of a photon. This is the leading diagram describing the classical interaction. And then you have more complicated Feynman diagrams with more complicated exchanges that give the quantum corrections to the classical interaction. However, not all quantum field theories are weakly coupled. For strongly coupled theories, generically speaking, we cannot calculate. Neither we can connect the basic fields to the notion of a particle. Interestingly, one of the theories of the Standard Model, which is quantum chromodynamics, also known as QCD, is strongly coupled at low energies. The lucky part with QCD is that it is weakly coupled as a theory of quarks and gluons at high energies. But at low energies, the quarks and gluons form bound states, and these are known as hadrons. The proton and the neutron are the only or most stable ones. Although the bound states are color neutral, they still interact rather strongly with an analog of the nuclear van der Waals forces that are short range. There are phases in QCD like that of the quark-gluon plasma that are made out of quarks and gluons, but they are strongly coupled. And these are studied by experiments using heavy ion collisions like the ones that you see in this picture from STAR happening at RIC. This phase, the quark-gluon plasma phase, is a very difficult regime because of the strong coupling. It's well studied by experiments, but first principles theory calculations are very difficult to come by. Supercomputers provide some help for QCD, but not for real-time dynamical processes so far. Let me now come to general relativity and gravity. As you probably know, between 1905 and 1916, Einstein tried to generalize his special theory of relativity to arbitrary changes of coordinate systems, and this is why this theory eventually was called general relativity. Now, special relativity already taught physicists that space and time are interlinked into a single entity, And this entity is Minkowski space-time with 3 space plus 1 time dimensions and whose geometry has no curvature. On the way in his endeavor, Einstein realized a rather deep truth, that looking for a theory of general coordinate transformation, this led to a new theory of gravitation that would extend Newton's theory via the principle of equivalence. The principle of equivalence states that locally a gravitational field can be removed by a change in the coordinate system, and the simplest and rather famous example of this is a person falling in a constant gravitational field in an elevator, and if one goes to his the reference frame of the accelerator, he feels no force. From early on, there were indications that Einstein's theory was correct and agreed with previous and subsequent experiments. Today, the theory has been tested thousands of times in very accurate experiments and has passed all such tests with flying colors. The GPS system alone that you're using in your mobile phones works with about a 1 meter accuracy and proves that general relativity in the vicinity of the Earth is correct to the 6th relative decimal point. The principle of equivalence states that all bodies fall the same way in the gravitational fields, and this has been tested to the 13th decimal point. In this graph, you see on this axis eta, which is a parameter which is the relative acceleration between two different bodies, and it's in logarithmic scale. And here are the various experiments over the years, starting with the famous Eötvös experiment in the beginning of the century and ending today with the rather famous also Eötvös experiments in Washington. General relativity predicts that there are gravity waves like there are electromagnetic waves. Einstein, who derived this early on, did not believe they would ever be observed because they were weak and because he also thought they were theoretical artifacts. It was Feynman in the 50s that persuaded relativists that gravity waves are observable. And this observation started a long-winded experimental effort which culminated, as you all know, a few years ago with their first detection, opening a new window in the observation of the universe. The speed of gravity waves was tested 3 years ago for the first time, and it was found to agree with the speed of light to the 15th decimal digit. The detailed dynamics of gravity agrees with general relativity to the 5th decimal digit. The central equation of general relativity roughly reads, and I wrote it here in very descriptive terms, on one side you have curvature, and on the other side you have energy density. The main field in gravity is the metric tensor of space-time. We call it G, with two indices, mu and nu, that take 4 values. These are the space-time indices. It's a 4x4 symmetric matrix, and it determines how we measure lengths between, for example, a point with coordinates x mu and a nearby point with coordinates x mu plus dx mu via this formula, that the length squared is the sum over the differentials with this matrix, the metric. So the metric determines essentially how we measure distances and therefore the geometry of space and time, and it is a dynamical variable. Basically, what the equation of general relativity says is that the curvature of this metric is affected by the energy density, and the energy density, of course, is affected by the curvature. So, in general relativity, the geometry of space and time is not fixed, but it's a dynamical field interacting with all the other matter fields, for example, the ones that describe the elementary particles. And already this is a radical departure from the Newtonian ideas of space and time. And it is for this reason that it was hailed as one of the revolutions of the 20th century. Like the theory of elementary particle, everything seems to tell us that the theory of general relativity is correct and needs not change. However, general relativity is a classical theory and does not yet have incorporated the rules of quantum mechanics. And the overwhelming majority of experts believe that general relativity will be eventually replaced by a more complete theory, we usually call it quantum gravity, that includes also the rules of quantum mechanics. Let me now come to cosmology. The dynamics and the evolution of the universe is the combined outcome of, on one hand, the theory of gravity, and on the other hand, the physics of elementary particles. In a sense, the physics of the very large, which is the universe, is determined by the physics of the very small, which is particle physics. And the ancient Greeks had a symbol of this for this idea. It was called Ouroboros, which means what the picture shows. It's a snake that bites its tail. The last 30 years, cosmological observations became very accurate and are capable in distinguishing the successful cosmological theories from the rest. There are essentially three main pillars on which the successes of modern cosmology rely upon. The first is the prediction of the expansion of the universe from general relativity. The second is nuclear synthesis. The prediction of nuclear physics are in agreement with measurements of the abundance of the simplest nuclei in the universe, which are helium and deuterium. And the third is the measurements on the cosmic microwave background radiation. The dominant cosmological theory, which we call it lambda CDM, describes quite well the current cosmological data. Here you see one of them, which is the map of the CMB as made by the Planck laboratory, who had measured the fluctuations in the cosmic microwave background with an accuracy of 9 significant digits. From these observations, one can calculate the spectrum of these fluctuations, something you see on this plot, density, intensity versus angle or multiple moment. And by analyzing this, it could be shown very recently that it agrees with the distributions of galaxies in the observable universe, establishing essentially a connection between the two. Therefore, both theory and observations concord that the structure in our universe, like galaxies, etc., has been seeded early on in the history from quantum fluctuations of the vacuum during the inflationary era. Another thing that we measure is the balance of energy in the universe, which, according to observation, is summarized in the following cosmic pie. We have ordinary matter here, which is about 5%. This is matter made out of the known elementary particles, like the ones we are made from. There is dark matter about 27%. We know for sure that it's like, it may be like ordinary matter, but it's certainly not particles we know. So it's outside the Standard Model. However, we have lots of ideas about it, what it could be, but it hasn't been directly observed yet. And finally, we have 68% of what we call dark energy. Now, the most mysterious content in the current universe is precisely this dark energy. It is mysterious, although the concept is very old. The simplest explanation of it is what Einstein already 100 years ago called the cosmological constant. This cosmological constant should be thought of as the energy of the vacuum that does not dilute as the universe expands. In fact, we can measure it, and it has been measured recently, by observing the expansion of the universe as it accelerates today. And from this, we have an observed value, lambda, the cosmological constant, has dimensions of energy square, and this is 10 to the minus 22 electron-volt square. Electron-volt, as a reminder, is essentially a unit of energy, which is characteristic of atomic interactions. Now, this is a very small scale, and if you compare it to the smallest scale in the standard model, which are in the neutrino sector, they're about 10 to the minus 3 eV. So you can tell that this is very small with respect to characteristic scales of particle physics. On the other hand, any quantum system contributes to the vacuum energy. Let me start from the simplest bound state system in quantum mechanics that most of you must have seen already, the harmonic oscillator. It involves a particle moving a harmonic potential which is proportional to x squared, the distance square. The spectrum of energies is given by the famous formula that you must have seen already, which is written here in terms of a natural number n. And if you make a picture of this spectrum, you have equidistant energy levels with a ground state energy given by n equals 0, which is h omega times 1/2. So the ground state energy is non-zero. If you don't have gravity, it's impossible to observe it. The only thing you observe in the absence of gravity, because of transitions, is essentially energy differences. However, we expect that this ground state energy and all energies, according to general relativity, that they should gravitate. By extending this very simple example to full quantum field theory, we know that in general, any quantum field theory has a non-trivial vacuum energy coming from quantum effects. It is in general non-zero unless there is a very special symmetry which is known as supersymmetry. In fact, this type of vacuum energy has a history which is interesting, and it's important also because we would like eventually to understand if it really gravitates. In fact, Casimir in 1948 predicted that this energy from the quantum vacuum fluctuations generates a force between two parallel metal plates. This force was measured for the first time in 1997 by Lamoureux at Los Alamos, and it was found to agree with the predictions of quantum field theory. Today, in fact, this agreement is better than 1%. Moreover, the fact that gravity is sensitive to vacuum quantum fluctuations has been experimentally verified with an accuracy which is better than 1 in 1,000. The conclusion of this is that quantum field theory that describes the three basic interactions gives us the opportunity to calculate the vacuum energy of the universe and to then compare it to that measured by cosmology. So we can calculate then the contribution of the standard model to the vacuum energy. And to do this, I would like to introduce the characteristic scale of gravity, which is known as the Planck mass, mp. It's given by this formula, which involves the three basic universal constants, the Heisenberg constant, the speed of light, and Newton's constant g. And if you put in numbers, you find an effective energy scale, which is 10 to the 28 eV over c squared. And mp, in fact, if you want to write the classical Newton interaction in terms of it, you can write it like this. The interaction between two masses m1 and m2 is given by m1 times m2 over mp squared, that's a dimensionless ratio, and then hc over the distance squared. So mp is the characteristic, the Planck mass is the characteristic energy scale of gravity, and it is 16th orders of magnitude larger than the largest energies we can create in the lab today, which are LHC energies. So now we can write more or less what the quantum effects of the standard model give for the cosmological constant. And they give a number, in fact, which is m Planck times c squared squared. And if you put numbers, as I said, this is about 10 to the 28 eV squared. Now, let's compare this number to the one that was measured via general relativity, which is here. If you take the ratio, I'm sorry, If you take the ratio, you find a difference which is 100 orders of magnitude. This is the largest error ever done in science. We do believe that this error is there because gravity has not yet been accommodated as a quantum theory. This is not the only clash between gravity and quantum field theory. There is another one which is quite famous, and I will come to it later on. This is the black hole information paradox. Of course, trying to accommodate quantum mechanics and gravity is something that started quite early on. This is an effort that has been done already since the 50s. And it was done by trying to do what we have done to make also classical field theory also quantum field theory. However, this line of attempts and thought, which has been going on for 60 plus years so far, has failed. Now, today we understand much better why this fails. The graviton amplitudes in the quantum theory behave very badly at high energies, much worse than standard quantum field theory amplitudes. And we understand today that the only way to correct their behavior is to have an infinite number of other particles of all spins going all the way up to infinity. But this type of quantum field theory with an infinite number of fields is a completely new concept. Fortunately, something like this popped up in an unexpected context. This was string theory, which is a theory of quantum strings, both open and closed. Now, a classical string, as you all know, is the same string that you have in guitars and other instruments. So string theory basically is to take a classical string, make it very small, and apply to it the rules of quantum mechanics. You all know that each string can vibrate in an infinite different number of ways. We usually call them normal modes. And because of this, the ensuing quantum theory that you would make has an infinite number of fields, each for each normal mode. Therefore, this would correspond to infinitely many distinct point particles. What is interesting is that in string theory, you always find a field that behaves like the graviton. Moreover, the theory is well defined in perturbation theory, which means at weak coupling, and in fact it is defined at weak coupling with diagrams which are analogous to Feynman diagrams that we use in quantum field theory. And in this picture here, you see the analogy between diagrams you will write in quantum field theory that are on the first line, which show interactions between particles, and similar diagrams between strings, here it's closed strings, which instead are two-dimensional surfaces. So string theory was introduced, in fact, in late 60s for a completely different reason, to describe hadronic physics. However, Scherk and Schwarz in 1976 realized that as there was a graviton in the spectrum, this should be a theory of quantum gravity. And it was checked that the existence of this infinite number of fields has the property which, as advocated, will make interactions at high energy finite, bypassing the shortcomings of standard attempts to define quantum gravity. So string theory provides a perturbative quantum theory of gravity. The graviton is one of many other fields that are present in the theory. Some of these fields, like the graviton, are massless. Most other fields are massive, and their masses are multiples of the string mass scale, ms, which controls also the tension of the string and is the characteristic scale of the theory. For other massless fields, in fact, they're similar to fields that we have already in the standard model. For example, there are gauge bosons, there are matter fermions, and there are scalars like the Higgs field. And this is the reason that sometimes we say that string theory unifies the particle interactions on the one hand with a quantum theory of gravity on the other. Unlike general relativity, string gravity is accompanied by several other fields. The most notable one is a scalar. We usually call it the dilaton. It is massless if string theory is weakly coupled, and it mediates a long-range interaction that generically violates the equivalence principle. Of course, classical extensions like this one with scalars of gravity have been discussed earlier on, and that was because people tried to write theories to extend general relativity. However, such theories are seriously constrained by experimental data. We have seen that general relativity introduced the dynamical geometry of space-time. Now, in string theory, the probes are not point-like like in quantum field theory, but they have a size. They're strings. And they see the geometry of space-time different than that of a point particle. For example, if space has features that are much larger than the sides of the strings, strings essentially act as points and they see the classical geometry. However, if space has features that are much smaller than the size of strings, then strings see a fuzzy view of the geometry. And to show you an example of this is given by a symmetry that one can find in string theory, which is known as T-duality. Now, T-duality applies when you have, for example, a circle. This is a geometry which has a size, and this size is the radius, r. Now, string theory cannot distinguish the difference between a large circle of radius r, which is, let's say, much bigger than the string length, ls, and another one which has a size, which r prime, which is much smaller than the string scale ls, and in fact, it is the inverse of r in units of ls. So string theory cannot see this difference. In fact, for strings, these two geometries are the same. And this is an indication that once things become smaller than the string scale, then the notion of geometry as seen by string theory changes. In fact, we know today that there is an infinite dimensional generalization of the notion of geometry in string theory, and it is encoded in what is known as two-dimensional conformal field theories. So at weak string coupling, the string geometry is semi-classical. You don't have large quantum fluctuations for the metric of space-time. This is because the coupling is small. Another thing is that unlike popular claims, string theory can be defined on space-times of any dimension. However, only when the strings live in 10 dimensions, then you can have solutions where the space-time geometry is microscopic and semi-classical. Let me now come to black holes. Black holes exist in any theory of gravity. They have a spherical horizon, which is marking the surface of no return, and in this picture is basically the boundary of this black disk, or black sphere in a sense. Starting with an observation by Christodoulou, in the early 70s, Carter, Bekenstein, and Hawking, in fact, found that the black holes of general relativity follow the laws of thermodynamics. The simplest black hole, in fact, is characterized only by one number, which is its mass. And in terms of this mass, they showed that the black holes have an entropy, and this entropy is proportional to m squared here, the mass squared, times the various universal constants, which is the Newton's constant, h bar, and c. It can be written in terms of the Planck mass as m squared over m Planck squared and a 4. And it can be written also in another very suggestive way as 1/4 the area of the horizon divided by the Planck length square, and the Planck length is a length scale characteristic of gravity, essentially proportional to 1 of the Planck mass. And if you put numbers, you find a very small length. It's 10 to the minus 35 meters. Holes don't only have an entropy, of course, they have a temperature. And this temperature, known as Hawking temperature, is proportional to 1 over their mass and the appropriate universal constants. Moreover, as these gentlemen first showed, they follow the standard thermodynamic laws that I mark here. The zeroth law, which says that in thermodynamics, it says that at thermal equilibrium, you have constant temperature, whereas here you get that at gravitational equilibrium, the horizon has constant surface gravity. The first law, which says that changes of energy of your system are given by temperature times the variation of the entropy plus the work that's done on your system. That applies also to black holes. And the second law, which says that the entropy can never decrease. And for black holes, it's the standard that, for example, if you have two black holes that eventually they fuse to make a third one, then the surface area of the third one is bigger or equal to the sum of the surface areas of the two black holes. Moreover, in 1974, Hawking had shown that if you treat matter around the black hole quantum mechanically, then the black hole evaporates. And it evaporates emitting black body radiation with temperature, the Hawking temperature. The presence of these laws in the gravitational dynamics of black holes remained a mystery for several decades. And moreover, it gave birth to the black hole information paradox, which is the direct between quantum mechanics and general relativity. And I can describe it in the simplest possible terms as you have matter in an initial pure state which collapses. It forms a black hole. The black hole continuously evaporates using Hawking radiation, and in the end, the black hole is gone. You're left with thermal radiation. Thermal radiation contains no information. It's in a mixed state. And quantum mechanics forbids that pure states evolve into mixed states. In fact, Hawking in 1991 bet against John Preskill that quantum mechanics must be changed because of this. Now, for those of you who have taken quantum statistical mechanics, which is the microscopic description of thermodynamics, they know entropy is a measure of the possible quantum states accessible to the system. If I call this number n, then entropy is essentially the logarithm of n. And the natural question in gravity, in general relativity and general in gravity, is what are the macroscopic states that produce the black hole entropy? The puzzle is sharpened basically because from quantum field theory we know that entropy is extensive. It always is proportional to the volume of your system. However, in black holes we have seen that it's not proportional to the volume, it's proportional to the surface area. So the natural question is, what is the microscopic explanation of the thermodynamic behavior of black holes? In fact, the microstates that are responsible for black hole entropy in string theory were counted for the first time by Strominger and Waffa in 1996. Their idea was the following. You start with weakly coupled string theory, where the coupling constant, the string coupling constant is much smaller than 1, and you construct a complex particle, a bound state made out of many elementary ingredients. In string theory, these ingredients are strings and d-branes, some solitons that exist in string theory, but that's not important. Now, if you make this very complicated composite particle, it has a given mass and a charge q. Now, if you are at weak coupling, you can use the effective quantum field theory that describes this bound state to calculate the entropy, which is the number of microstates. That is, in how many ways you can put these particles together to create an overall bound state that has mass m and charge q. So this is doable, and it can be done, and this has been done. Now, this you can do, but the question is, what does it have to do with black holes? Here comes the crucial observation. If now you take your theory, your string theory, and you take the coupling constant to be much bigger than 1, you change the coupling constant, then the particle, the bound state you made, puffs up and it becomes a black hole with the given mass and charge. You can understand this a little bit because by taking GS, you make gravity, in a sense, stronger, and then this particle would generate long-range gravitational fields that there will be these of a black hole. So if you trust the number of states you counted, and this gives you the entropy at weak string coupling, you can find what it becomes at strong coupling when this is a black hole. And in fact, it was found that this answer, which was calculated microscopically, agreed with the Bekenstein formula for the entropy of black hole. However, this argument contains a leap that's not allowed in general. You cannot take a calculation in a theory at weak coupling and take it for granted and apply it to strong coupling. Moreover, as I told you, if you try to do this calculation at strong coupling, both in quantum field theory and in string theory, we do not know how to calculate. However, the trick here, and that was the smart thing that these guys did, is that they looked at some very special black holes that have zero temperature, but they have non-zero entropy. Now, such black holes can be shown to have a very strong symmetry, and this is supersymmetry. And in such a case, you can show that the weak coupling calculation gives the same result as the strong coupling calculation. And therefore, you have something that looks like a miracle. The microscopic calculation gives an entropy that agrees with the Bekenstein entropy of a black hole for strong string coupling. Now, people didn't stop there, but they tried something even bolder. Then they considered a bound state which would correspond to a black hole now which has a very small temperature. And the reason now you need a very small temperature is that if you want to test, for example, the Hawking evaporation, you cannot do that with a black hole at zero temperature, because at zero temperature, no body has thermal radiation. So you need to have a small temperature, and then you can test Hawking evaporation. So people calculated the decay rate in string theory for the bound state at weak coupling, and they found, surprisingly, that it agrees with Hawking's formula for the decay rate, which was calculated from gravity, and it would be valid for very strong string coupling. Now, this agreement was a mystery, basically because when the temperature is non-zero, supersymmetry is broken, and it was supersymmetry that protected us in order to extend our results from weak coupling to strong coupling. However, the fact that although this calculation was not protected, it agreed, is the first hint that led eventually to what is known today as the ADS-CFT, or the holographic correspondence. So we have seen that although in standard matter theories entropy is proportional to the volume, for black holes is proportional to the horizon area. And this already led people to the suspicion that in gravitational systems like black holes, the entropy is projected holographically on the surface area that surrounds the volume of interest. And it was 't Hooft who first proposed in 1992 that this holographic property, we call it holographic, of course, because that's how holography with lasers works. You project the details of a solid picture into, of course, a screen, that this holographic property should be a generic property of any quantum gravity theory. At the time, of course, that this was proposed, it was not at all clear how this would be realized. And it was this investigation of black hole entropy and the information paradox that in 1998 led a young physicist, Juan Maldacena, to propose a correspondence which I will put it in today's more general terms. And this correspondence says that essentially string theory is equivalent to quantum field theory. Or to put it in a different way, string theory and quantum field theory are two different views of the same object, or two different sides of the same coin. Let's see how this works in the prime paradigm for this correspondence, which was the first that was originally analyzed. And this paradigm, in fact, involves, first of all, a four-dimensional quantum field theory. It's called N=4 super-Yang-Mills theory. It's not important what it exactly is, but I will describe it a little bit. It resembles the theory of strong interactions, quantum chromodynamics. It resembles it in the sense that it has gluons also, which are the gauge bosons that are mediating the interactions. It has in general NC colors, although quantum chromodynamics has 3 colors, but here we keep the number of colors arbitrary. It has also a few other fields. It has a larger symmetry than quantum chromodynamics. It has maximal supersymmetry in 4 space-time dimensions. And it has also a special property, which is also related to the large supersymmetry. The quantum effects in that theory do not make its coupling constant, its strength of interactions depend on energy, as it happens in QCD and in all other quantum field theories. And in fact, this theory is a theory without masses and without any scale. It's a scale invariant theory. And its only parameter, except for the number of colors, which is a natural number, it's its coupling constant that I denote by lambda, and the coupling constant usually controls the strength of the interactions. When this coupling constant is very small, the theory is weakly coupled, perturbation theory is useful, and we can use it to calculate using Feynman diagrams. Therefore, in this regime, physics is calculable. However, if this coupling constant is large, the theory is strongly coupled, and all hell breaks loose. We do not know how to calculate. So based on results coming from stringy black holes, Madlacena conjectured in 1998 that this theory, n equal 4 super Young-Mills, in 4 space-time dimensions, is equivalent to a string theory that lives in 10 dimensions, and the geometry of these 10 dimensions is a concrete geometry of a space which is known as ADS5 cross S5, and I will describe here what this is. So this geometry contains 2 5-dimensional geometries. The first one is S5. It's the 5-dimensional sphere. It's a highly symmetric 5-dimensional geometry with constant positive curvature, finite volume, no boundary. It's basically the 5-dimensional analog of the 2-dimensional sphere that everybody knows as the boundary of a ball in 3 dimensions. And the de Sitter 5 is 5-dimensional de Sitter space. This is also a highly symmetric 5-dimensional geometry. But this time it has constant negative curvature, it has infinite volume, and it has a boundary. And the remarkable fact in this correspondence is that the 4-dimensional theory of gluons is equivalent in all respects to a 10-dimensional theory of strings. Now, this equivalence, we call it duality, because it is 2 different descriptions for the same thing. There is another remarkable fact, in fact, in this correspondence. It's the correspondence of the parameters of the 2 descriptions. For example, the string coupling constant, which tells us how strongly strings interact, is 1 over the number of colors. Therefore, if the number of colors is very large, much bigger than 1, then the associated string theory is weakly coupled, and we can more or less handle it. The other is the coupling constant of the super Young-Mills theory. It is given by the ratio of the 4th power of the radius of a de Sitter space to the 4th power of the length of the strings. And now we can observe the following, that if the quantum field theory, the Young-Mills theory coupling constant is very small, then, as I told you, we can calculate in quantum field theory. But in string theory, when this is very small, it means that the string length is much bigger than the radius of ADS. In that case, the strings are very big, the string theory is very stringy, and we cannot solve it yet, in fact, although we're missing serious progress. So, on the other hand, when the coupling constant in quantum field theory is strong, as I told you also, we cannot calculate in quantum field theory, but in this case, from this formula, the string's length is much smaller than the radius of the ADS scale. And in this case, the strings, you can approximate them as, because their length is very small compared to the radius, as point-like, and therefore you can approximate the string theory by its point-like limit. And this point-like limit is a classical generalized gravity, because it, apart from the gravity, it has also other fields. It lives on the same manifold, that's ADS5 cross S5. And this theory we can solve using the techniques of general relativity. So the conclusion is that at weak quantum field theory coupling, we can use quantum field theory to calculate, and at strong quantum field theory coupling, we can use the gravitational description to calculate. However, you can ask yourself, if this is the case, how can we tell that the two descriptions give the same theory if we cannot calculate in both cases in the same regime? The reason that we have good reason, of course, strictly speaking, this is not known. However, because we have a large amount of supersymmetry here, there are lots of results, as I mentioned also earlier, that we can calculate at weak coupling and we can extrapolate at strong coupling and they don't change. And after almost 20 years, we have many, many calculations of that type that are compatible with this radical conjecture, even beyond this particular example. Formally, however, proving the equivalence is a very difficult and open problem. Let me tell you a few words about the geometry of an de Sitter space and how it is related to holography. So, in general, I will consider a de Sitter space in p+1 dimensions, which topologically is a generalized cylinder. Here I have a picture of the three-dimensional de Sitter space. So it has one dimension here, which is along the cylinder, and this is time. And then I have the cross-section, which is two-dimensional, and it's a disk. And the disk, as you can see, has a boundary, and the boundary is a circle. And the boundary of anti-de Sitter space is the surface of the cylinder, whereas its interior is the interior of space. And typically, the radial direction that goes inward, we call it the holographic coordinate. So in other directions, more or less, you have a similar picture, which is generalized. For example, the boundary of which was an S1 here, a one-dimensional circle, is in general a sphere in p-1 dimensions. The radial coordinate is always the holographic coordinate. And therefore, the full boundary of a de Sitter, five-dimensional de Sitter space is R, which is time, times, in this case, a three-dimensional sphere. This is a four-dimensional manifold, and it is the space on which the dual quantum field theory lives. And when we have the total 10-dimensional space, which is under the Sitter 5 cross S5, in which the string theory lives, the boundary of this manifold, since S5 has no boundary, is again R cross S3, and it is on this boundary, which is four-dimensional, that the dual quantum field theory lives. Therefore, we get a picture that looks like this. This is at a fixed time now. You have a boundary, which is an S3. Of course, it's S2 in this picture, but you can imagine S3 in 5 dimensions. And it's on this boundary that the quantum field theory lives. And inside this boundary, you have the strings. So string theory, quantum field theory correspondence conjecture that I'm describing realizes the idea that the quantum theory of gravity that's in the interior is holographic. It's projected on the quantum field theory, the boundary. Moreover, the quantum theory of gravity, which is the string theory in the interior, has one and sometimes more dimensions than the equivalent quantum field theory at the boundary. And this is why also we call this correspondence also the bulk boundary correspondence or the holographic correspondence. So we always have a dual pair, and we have a geometry which has a boundary. The quantum gravitational theory lives in the interior of the geometry, the non-gravitational theory lives at the boundary, and the two descriptions are equivalent. So let me now come back to black holes and how they fit the holographic correspondence. What we have seen so far is that the geometry of ADS5 cross S5 describes the ground state of super Young-Mills theory in the gravitational hologram description. The obvious question one can ask is what geometry would describe the thermal ensemble of super Young-Mills theory? And not surprisingly, this is precisely the ADS black hole geometry. There is a black hole solution in ADS space, and it is this solution that describes the thermal ensemble of super Yang-Mills theory. It's more or less portrayed here. This is again the boundary, but now in the interior we have a black hole at the center with its appropriate horizon. Now, once we understood this, we can explain the black hole entropy. It is the entropy of the dual quantum field theory in the thermal ensemble. Not only that, we can do better than that. If we take the thermal ensemble in quantum field theory and we perturb it a little bit, then the equations that describe this are the relativistic hydrodynamic equations of the appropriate quantum field theory. Similarly, the same thing we can do by now perturbing the horizon of this de Sitter black hole, and people manage to show that what you obtain are exactly the same equations. The relativistic hydrodynamic equations also describe small perturbations of the black hole horizon in a de Sitter space. So the black hole information paradox in its original form is now clear how it will be resolved. The formation of the black hole and its subsequent evaporation, which is central to the black hole information paradox, can now be mapped to a scattering experiment in the dual quantum field theory. You have stuff that comes in at the boundary, they do something in some region, and then they go out again. Since the dual quantum field theory is unitary, we know from first principles in quantum field theory that the scattering is unitary. The probability is conserved, and if the original state was a pure state, the final state has to be a pure state. And it's as simple as that. Of course, at very high total energy, if we have a state at very high total energy, a generic pure state is very close to a thermal state. In fact, this is stated by Lloyd's theorem, which also states how close that is. And it is precisely this theorem that explains now why black holes look thermal classically. But they look approximately thermal. There are tiny corrections to their thermality, and we can estimate that these corrections are of order e to the minus s, where s is the entropy. And the entropy for real black holes is a huge number, is an exponential of an exponential. And these tiny corrections, on the other hand, are important because they, although they are very small, they provide the correlators in the Hawking radiation that restores the finer information. Of course, this doesn't solve everything. There are several mysteries that still remain, like the firewall paradox. But scientists, at least today, feel confident that they are on the right track. I told you that in 1991, Hawking bet against John Preskill that information is lost and quantum mechanics must be changed. However, following the proposal of the bulk boundary correspondence, 2004 Hawking conceded defeat. That information is not lost if gravity is described by string theory, and therefore he paid his lost bet to John Preskill. So let me conclude. From the studies of the phenomena that I mentioned here, our understanding of gravity has radically changed. The notion of space-time dimension is dynamical. It emerges from the dynamics. It's not defined a priori. Gravity itself is emergent, and the graviton and other gravity sector fields are composites of quantum field theory fields, like generalized gluons. At very short distances, the natural degrees of freedom are the generalized gluons, not the gravitons. The gravitational physics is holographic and has instances of non-locality. Of course, there are still subtle issues which remain, for example, with the information paradox, that need to be understood, and there is vigorous research in this direction. I haven't talked about that, but I would like to mention it here. There is a deep connection between holography and quantum information. In holographic theories, one of the key elements of quantum information, which is entanglement entropy, becomes geometric via the Ryu-Takayanagi formula. And it is believed that the semi-classical geometry of gravity is born out of the strong entanglement of the underlying quantum mechanical degrees of freedom. The cosmological constant problem that I mentioned earlier still remains murky, but we understand now that holographic gravity does not only couple to vacuum energy. Dynamical gravity, in fact, also couples to the non-dynamical metric of the dual quantum field theory. And we can show that if this metric is flat, then a non-zero cosmological constant can be compatible with a flat dynamical metric. However, there is still much more left to be understood. And with this, I would like to thank you for your patience. So if there are any questions, I would be happy to attempt at least to answer them.
So sorry, I had some problems with my microphone that it wasn't detecting. Can you hear me now?
Yes.
Okay, amazing. We do have quite a few questions, actually.
I don't mind answering as many questions as at least I know the answer. I'm sure most of them I would not know the answer.
I mean, the first one was regarding the string length scales. And you say, like, whether it can be related to other fundamental constants. So you have, of course, you mentioned the ADS conformal field theory correspondence, where it's related to the inverse coupling strength, right? But in general, like, is that where we generally get the string theory length scale, or?
It depends how you define string theory, in fact. Let me say a couple of words about that. First of all, the standard string theory we know and we have studied for many years, which is known as fundamental string theory. In that theory, the string length is an input parameter, is what defines the theory. And therefore, you can relate it, of course, to observable quantities in principle, but it is what defines the theory. However, fundamental string theory is not the only string theory there is. There are many string theories that you can call them effective, but that's what we thought until now. But they're not as effective after all. For example, if you take a gauge theory like quantum chromodynamics, which is something we can eventually observe, we know that in quantum chromodynamics also we have strings. These are strings of chromoelectric flux. These have things that we have analyzed on lattice calculations on computers and gauge theory. And they resemble in some respects, in fact, the fundamental strings that we study in string theory and generalize them. And in fact, the strings that exist in N=4 super Young-Mills are of this second type. And this is also the reason that string theories of the type that appear in N=4 super Young-Mills, we cannot solve them even at weak string coupling because they have more complicated properties and because they are related to gauge theories. Although, as I said, we're making a lot of progress recently, and we are on the way of solving also these theories at weak string coupling. Now, so how the string scale is related to other observable quantities, it depends on what type of string theory you have. Let me discuss the string theory of QCD, which is something very close to what we measure. In QCD, there is a string scale, which in general, if you define QCD via the QCD coupling constant, then the string scale becomes a function of the string coupling constant, or the string coupling constant is a function of the string scale. And in QCD, we have measured both, and therefore we know what they are. I don't know if this answers the question.
I think so. Thank you very much. Then the next question is regarding whether this ADS-CFT correspondence is just a calculational tool or whether it corresponds to reality in some way. Especially given that the universe isn't ADS.
Let me first say that I know this is not ADS. In fact, we don't know if the universe is not ADS. We have a description of the universe, which is rather simple. Usually we use the simplest description that agrees with what we understand and we measure, which of course is not ADS. But we don't know if you look much farther than what we look now, there is an ADS boundary. That's, in fact, an open problem. And it's an open problem not only, of course, experimentally, but it's an open problem theoretically, because it's not clear yet how you can accommodate de Sitter regions inside the ADS space. In principle, it's possible, but we don't have a good workable example. Therefore, first of all, it's not excluded that eventually the universe has an ADS boundary. We don't know. It may not have. That's one thing. Second, sorry, I forgot the beginning of the question. Yes, you were saying to what extent the two dual descriptions are real or calculational tool. In fact, a duality is telling you that what a description is telling you is not necessarily real. You have one thing. Now, this one thing is the common theory that's described by the two descriptions. But you have two ways of looking at it. And on the other hand, these two descriptions can give you intuition only in specific regimes of the theory. For example, if you take Super-Yang-Mills theory, which we describe using quarks and gluons. Now, if you go to weak coupling, this theory, of course, is a collection of theories for different values of the coupling. You have weakly coupled Super-Yang-Mills, you have strongly coupled Super-Yang-Mills. These are different theories. So, if you take a Super-Yang-Mills theory with weak coupling, then we know that if you calculate using quarks and gluons, gives you, first of all, the right answer, but moreover, it is close to what the theory looks like if you do experiments. That is, you will see quarks and gluons at least in a Gedanken experiment. On the other hand, if you take this same theory and you take it to be at strong coupling, the quarks and you try to describe it with quarks and gluons, and suppose you are strong enough that you can solve it, what you will find cannot be easily intuitively explained in terms of quarks and gluons. In fact, it can be easily intuitively explained using strings. So we have two pictures of what such a duality is telling you. It gives you two different pictures, and each one of them applies better to some regime of the theory. Or if you are strong to solve them both for all theories, they give you two equivalent descriptions that describe the same thing. And then when you ask, what is reality? In fact, there's no answer. Both of them are as real as the other one because they give a complete description, if they do. I don't know if this answers your question.
Yeah, I think it does. It was very clear. Overall, you've been very clear at explaining, and your warning about English was completely unnecessary. You've been a very clear speaker this entire time. I have a question regarding, you say in conventional quantum mechanics, you have the volume law scaling. But don't we have certain states of matter, like many-body localization, where we see like entropy scaling as an area law? Like, could it be that black holes are simply some non-trivial state of matter where we don't have volume law scaling of entropy, and then we don't need this whole machinery?
Okay, there is no simple answer to that question, but let me order a few points that I understand. First of all, if you have a system whose dynamics is the appropriate dynamics for its dimension, because as some of you may know, sometimes for very special systems, especially strongly disordered systems, there is dynamical reduction, the Parisi-Surmals mechanism. And although you have a system, let's say in 3 dimensions, its dynamics is like 1 dimension. So in such systems, obviously, you can misinterpret what happens. So that's one thing. But this may apply to many body localization, at least in higher dimensions, but I've never seen it claimed. So there is one thing when the dynamics of a system has a dimensional reduction. But this has nothing to do with what I'm talking about. In fact, let's now come to an example of Yang-Mills theory, right? And let's see how holography explains this. Let me take 4-dimensional Yang-Mills theory, which is 3 + 1 dimensions, so space is 3-dimensional. So you take some, volume, and you would expect in this theory that the entropy will be proportional to the volume. And indeed it is. Now, how does this fit black holes? Remember that in NCOR4 super Yang-Mills, the gravitational description is in 1 dimension more. In fact, it's in 6 dimension more, but as the 5 dimensions are compact, they don't count for this. So it's in 1 dimension more. So the black hole lives in 5 dimensions. And the horizon of a 5-dimensional black hole is 3-dimensional. And this is why the 2 results match. To put it also differently, in ADS space, if you calculate volume near the boundary and you calculate area, they are proportional to each other. That doesn't happen in flat space. So there is no puzzle from this point of view, but in order to see that there is no puzzle, you have to take gravity 1 dimension up. I don't know if this answers your question. In fact, let me come back also to the original question. Therefore, there are systems that have dimensional reduction, and there you have to understand that this happens, and then the entropy, of course, would have to follow the appropriate law that's appropriate to the lower dimension. But otherwise, in systems that don't have dimensional reduction, there is no puzzle, because the holographic description that sometimes we apply, in fact, today with rather quite a success, but as toy models, on the other hand, to condense matter systems, there's no puzzle because the dual gravitational theory has 1 dimension more. That's basically the answer.
Okay, that makes sense. Thank you very much. One of the people in the audience is asking regarding, you mentioned in the start that supersymmetry means that a quantum field theory can have has no 0 point energy. Could you expand a bit on that?
If you have a supersymmetric theory, and this is a theory where pretty much fermions and bosons are mapped to each other, it is known that the sign, at least at weak coupling, the sign which different particles contribute to the vacuum energy depends on whether they're fermions or bosons. So bosons have a minus sign and fermions have a plus sign. Sorry, bosons have a plus sign, that's the harmonic oscillator. If you take a fermionic harmonic oscillator, it has -1/2 h omega. And therefore, supersymmetry is such, because it pairs bosons and fermions, that it makes certain that all these contributions cancel. The reason that this is not good enough to help us with the problem, although it can make the discrepancy much less, is that we know that in our world, at our energies, there is no supersymmetry. Or if there was supersymmetry at high energies, it must be broken now. And therefore, we still have the problem.
Okay, thank you very much. And I think we have time for one more question, I think. 2 seconds. Let me just have a look at something one person asked regarding the I'm not familiar with this paper, but one person mentioned a paper by Ahmed Almhairi, Juan Maldacena et al. Concerning the resolution of the information loss paradox. Are you familiar with this?
Yes. Yes. So the question is, what do they do, or how?
Whether you could make any comments on their paper, if you are aware of it.
There are several papers, in fact, in that direction, starting with a paper by Pennington. And the paper you mentioned, in fact, has contributed importantly. What these people do is they put another brick towards our understanding on how the information paradox is resolved. Because, as I said, we understand more or less what happens for many of the things, but that doesn't mean that we always can calculate all of them. I'll tell you why in a moment, although you can, because I've seen a glimpse also in another question that points to the same thing. There is, in fact, one paradox, one feature of the paradox that was already pointed out by Page long time ago. If you take the original calculation of Hawking and you look at what happens to the entropy of the outgoing radiation, according to the Hawking calculation, in fact, the entropy of the outgoing calculation rises linearly until the end. And therefore, you end up with maximal entropy and loss of information. However, Page has said that if the information paradox is resolved as we now believe, in the same way it's resolved when you have a piece of carbon that is, of course, in a pure state, and then you burn it. And in the end, you get just nothing left, and if it's pure carbon, and thermal radiation. Of course, that is described by quantum mechanics. We are convinced. We do not expect that the information that was stored in this piece of carbon is lost. And we know, although we cannot calculate explicitly, but we can argue that the information is apparent in the end as tiny correlations of the type E2SS I mentioned before among the radiation that is emitted. Now, if you follow this, then we know that for such systems, what happens with the entropy of the outgoing radiation, in the beginning it rises linearly, and somewhere in the middle, at the time known as the Page time, it turns around and then goes down to zero. So when the full process is ending and there is nothing left from the black hole, you expect that the entropy should be zero because you started from a pure state. And you should end up with a state which is pure. Now, what the calculations you are referring to are doing is, it was, of course, in principle, if you can compute using quantum mechanics, or if you compute using the quantum field theory in our holographic example, that's what you expect to get. But the question is, how do you get that from the gravity theory? What was found, in fact, recently is that this calculation can be done in a gravitational theory by considering saddle points in the calculation of the path integral, which people did not consider before, in fact, which are called replica saddle points. And then if you do that, then you do get more or less the Page curve. That's what was done in this type of thing. So to answer also to another question that was asked earlier, we do believe that what happens for a burning piece of coal now happens to black hole. But the problem, of course, is that both for a burning piece of coal and black holes, is very difficult to have concrete calculations that show this quantitatively. On the one hand, for a burning piece of coal, everybody believes it's true, although we don't have a precise calculation. Whereas for black holes, until now, we didn't have necessarily very good reasons to believe that this would be the case. But slowly we're edging there. I don't think we will ever have a complete calculation, because this may be impossible to do, but at least we will have enough individual calculations here and there to convince us that this is how things are happening. There is much more to be done in that case, and there is also the firewall paradox, which I didn't mention, neither I will explain now, but I should say also that even in this case we have a couple of guesses, but we don't have yet hard calculations to tell us what's the right guess.
Okay, thank you very much. Then I think as the last question, this is another rather technical one regarding somebody was asking regarding something called Horava-Lifshitz gravity, and they're asking. Let me just see if I understand their question.
Can you read the question?
Yes. What can you say about Horava-Lifshitz gravity? I mean, what's your opinion about it if we take black hole solutions in 5D Horava-Lifshitz gravity?
Okay. Let me say a couple of words. Horava-Lifshitz gravity is a non-relativistic theory of gravity that was introduced by Horava in, I don't know, 10 years ago, 10 years ago, with the motivation that he writes a field-theoretic theory of gravity in 4 dimensions, which is power-counting renormalizable, unlike general relativity, which is not power-counting renormalizable. And now this is non-relativistic, so at high energy, this is a non-relativistic theory of gravity. People have made modifications to it, and now at least one can present a theory that at least it agrees with all the data we have now. It has a scale, and of course one needs more experimental data to check whether it's correct or not. The claim that this is fully renormalizable with a quantum computation and not just power counting has been verified for the 3-dimensional case, but it's open for the 4-dimensional case. So a priori, of course, it is a theory that has to be taken seriously and be examined. There are many unsolved problems, of course, in this direction, but when I come to black holes, in a sense, are more difficult in that theory because of the non-relativistic nature of gravity and because of some other reasons that I cannot explain here, it's much more difficult to interpret what's the analog of entropy and what's the analog of the information paradox in that theory. So we don't know, and I presume maybe one day we will know.
Okay, thank you so much for all of your time and for your wonderful presentation and for answering all our questions. I think it's a good time to wrap up now. So for everyone, thank you so much for staying through the question session, and thank you so much to you, Elias, for coming here and giving a talk. It's been a real pleasure.
Thank you to all of you, and to you in particular. I should add that I presume people may have more questions. They
Yes.
can email me, and if I have something to say, I will answer back. So thanks to all of you, and have a good evening.
Thank you, you too.